Hello and welcome to the last talk that we've got for the Orkney Aviation Festival for this evening. And we have to say a very big thank you very much to the speaker who filled in at very, very short notice. And he is Andrew Ray, the Professor of Engineering at the UHI, the University of Highlands and Islands. Thank you very much to Andrew, who jumped into the breach to provide this talk for us. It's called Technical Considerations and Challenges in Sustainable Aviation. There will be a chance for questions later on after the talk, so if you have a question, please put it in the comments section or below the picture there on YouTube, and we'll try and get Andrew lightly grilled at the end of his talk. Now, he will be given an inside view on sustainable aviation and the detail behind the different platforms, including some pros and cons around each one. So I'll hand over now to Professor Andrew Ray. Andrew.
Thanks, Dave. Good evening to everyone. Thank you very much for the chance to talk here. So as Dave mentioned, I've put together a presentation that's been pulled together from a variety of sources. So if it looks a bit bitty, then you'll understand why. So as Dave said, I'm going to do a personal evaluation of some of the challenges that sustainable aviation faces. If you've seen the other talks today, you'll have seen more about the work that's being done in Kirkwall and in the islands around sustainable aviation. I'm going to touch on some of that, but I'm also going to talk about the application of low carbon propulsion to larger airframes as well. So next slide, please. So I'm going to cover three things. Start off with some physics. Hopefully we won't be teaching you too much to suck eggs, but it explains some of the concepts I'll be talking about later, and then the implications of those physics and of the alternative propulsion systems on aircraft design, which is my background, and then look at the variety of alternative powertrains that are being proposed at the moment and the pros and cons of some of those. Next slide, please. So starting off with some physics and pressure, if you just scroll through, I think it's 3 or 4, please. So the Earth's atmosphere is split up into regions demarcated by height. So the one that occupies most of us is the troposphere. So that's up to 10 kilometers in altitude. But most aircraft fly in the stratosphere. So the A380, which is the second picture up from the bottom there. I think there's one more, please, John. That is the last one. That's it. Thank you. Cruises at around 30,000 feet, plus or minus a bit, which is where you'll go in most airliners these days. Everest is about 8 kilometers high, and One of the few exceptions as far as aircraft was concerned was Concorde, which flew at 60,000 feet for a variety of reasons. Obviously, as you go up in altitude, the air gets thinner and the density decreases, so the mass of the air is changing, which has implications for lift, for drag, and for temperature, and I'll come on to those. So the density of air is highest closest to the Earth, and it decreases as you go up in altitude. And about 80% of the mass of the atmosphere is contained within the first 10 kilometers altitude. That's the troposphere. And only 19% of the atmosphere mass is in the next 40 kilometers of altitude, which is the stratosphere. Next slide, please. So if you imagine a column of air extending from above your head to the edge of the atmosphere, next slide, please. So each cubic meter of air has a mass of just over a kilogram at sea level, and that decreases. Next one, please. And again, please. So that reduces, as I said, so to the edge of the troposphere at 10 kilometers, that's more than halved. It's down to 0.4 of a kilogram per cubic meter. And then in the middle of the stratosphere, it's right down to 0.018 of a kilogram. So you can see how quickly the density reduces. If you were to integrate that mass from the top of your head all the way to the edge of the atmosphere, next slide, please. It's equivalent to 7 Ford Focuses. Other small family cars are available, but that's quite a weight sitting on your head. Obviously, humans are designed to cope with that pressure, but if you were to climb a mountain, so if you would go up to the top of Everest, it's equivalent to only 2 family cars. So there's a massive difference in the density of the air as you increase in altitude. And of course, you'll all be aware of how that pressure varies. If you climb a hill in a car, your ears pop, or if you go up in an airplane, your ears will pop, and that's to do with the drop in density and therefore the drop in mass above your head and the pressure. Next slide, please. So the other thing that varies with altitude is temperature. So as you move away from the Earth's surface and the heating effect of that surface, the temperature drops, and it drops quite significantly to well below 0 as you go up in altitude. There's several different temperature scales that we use in modern. We use degrees Celsius and Kelvin. Fahrenheit is an interesting one. I think 0 Fahrenheit is the freezing point of brine, and the upper point was Mrs. Fahrenheit's armpit, which is probably not the most scientific of datum points, but I think it was changed shortly afterwards to come up with something that was a bit more constant, perhaps. And temperature is important because something like Concorde, which flies very fast, has a lot of what's called kinetic heating. So the friction of the air on the surface of the aircraft heats it up. And so the reduction in temperature at altitude helps counteract that kinetic heating and stops the aircraft expanding too much or getting too hot. And I'll touch on friction a bit more shortly. Next slide, please. So aircraft wouldn't fly without friction. Any 2 objects moving adjacent to each other will have some degree of friction, and air is no different. It may feel nice and thin and gaseous, but actually there is friction. As the wind blows, you'll have felt it on your face. And what that does is reduce the speed of moving air close to a surface. And the area that's affected by that friction is what aeronauticists call the boundary layer. And that's a significant part of aircraft design is understanding and adapting that boundary layer. Next slide, please. So it tends to be 2 states of a boundary layer. On the right-hand side, it's a diagram of a wing, and the boundary layer exists in 2 states. It starts off nice and smooth, what we call laminar. It then goes through transition to a turbulent boundary layer, so it's more messy. So the picture on the left shows a boundary layer on a flat surface. It starts off nice and linear and smooth, as in laminar, it then, due to the effect of roughness or other turbulence, becomes unsteady and turbulent. Next slide, please. So it's really important to understand that boundary layer and the effect of friction, because it affects how the air goes round or across a surface. And aerodynamicists spend a lot of time worrying about the state of a boundary layer and how they can get the most from it. A turbulent boundary layer, so the one on the right there, is actually more useful sometimes. It has more drag, but because it's chaotic, it pulls in energy from outside the boundary layer, and that energy gives it the ability to go around corners, which is useful if you've got an uneven shape that you want the air to go around or persuade it to go around. Next slide, please. Yeah, scroll through a couple for me, please, John. Yeah, that'll do. That's it. Thank you. So pictures on the left-hand side there are of the same sphere in a wind tunnel, with smoke showing how the boundary layer on the sphere, so the air is moving from left to right. On the top sphere, we don't do anything to the boundary. We let it separate from the sphere to form a wake. And you can see that separation of the air from the back of the sphere occurs roughly at the equator of the sphere, and so you get a big, large turbulent wake behind it. In the bottom picture, a thin wire has been added onto the sphere, and that causes turbulence. As I said, a turbulent boundary layer has more energy, which means it can go around corners more effectively. And I hope you can see that the wake of that bottom picture is much smaller than the one on the top. And that's the reason why golf balls have dimples. Obviously, it's not. It's quite tricky to put a wire around a small ball, especially if you play golf as badly as I do. The ball will be spinning, so the wire won't be in the right place. But by putting dimples on it, we create that turbulence, reduce the wake, and the ball will go further. Next slide, please. So the formation of that boundary layer and the wake are significant contributions to the total drag of an aircraft. So this is a tree of all the drag components on an airplane. So on the left-hand side here, looking at subsonic aircraft, the skin friction is the boundary layer. Form drag is the shape, so whether it's streamlined or not, and then interference drag is caused by junctions, for example, where the wing meets the fuselage or where the engine pylon meets the wing. So there are several sources of drag, all of which need to be minimized. Next slide, please. So just a little schematic diagram to show how streamlining can reduce drag considerably. So if you take a flat plate and put it sideways onto the air, as the top picture shows, you get a very large wake and you get a lot of drag. If you progressively make that flat plate more streamlined, so turn it into a sphere and then a teardrop and then an airfoil shape, you can get down to less than 5% of the drag of the flat plate, even though it's got the same frontal area. So that's a lot of the reason why cars are streamlined, why aircraft are streamlined where they can be. Next slide, please. So in straight and level flight, the lift you need to maintain straight and level flight will be equal to the weight, and the thrust from the engines will need to equal the drag of the aircraft. And the lift and the drag both vary with what the aircraft is doing. So the graph on the picture there is what's called a lift curve slope. At low angle of attack, so this angle of attack is on the bottom axis and lift is on the vertical axis. So at low angle of attack, we have sufficient lift to keep the aircraft flying straight and level, and it's not doing anything too silly, so the drag is quite low. Next slide, please. If we pitch the aircraft up, maybe to climb, for example, we increase the angle of attack, we also increase the lift, and therefore also increase the drag. Next slide, please. If you take that too far, you can stall the aircraft, so the lift drops, but the drag goes up massively. So the lift drops, and so does the aircraft. Next slide, please. So lift and drag are related, and so an evaluation of the efficiency of an aircraft is the lift to drag ratio. And the bottom left-hand picture there shows the lift increasing with angle of attack as in the previous slide, and on the right shows how the drag increases with angle of attack as well. So both increase with angle of attack, but they do it differently. Next slide, please. So as you plot lift against drag and angle of attack, you find out there's a sweet spot, which for most civil aircraft is around about 2 degrees angle of attack. So most wings on most airliners are bolted onto the fuselage at about 2 degrees because that's where they operate most effectively in cruise. Next slide, please. So as I said, that lift to drag ratio is an important metric for determining the efficiency of an aircraft. So the graph here shows you how the aerodynamics of an aircraft have improved over the last half a century. So starting with the A300 in 1975 had a lift to drag ratio of about 14.5. And that improved through the 80s and 90s until the A380, and aircraft like the 787 and the 777 now have a lift to drag ratio of about 20. So a huge increase in lift to drag ratio. What that means is that for the same lift, the drag has dropped by about a third. And that's good news because you need less thrust to overcome that drag, so you burn less fuel. But this was done not so much from a sustainability point of view, but more from reducing cost point of view. So that's one of the things that's changed in the last decade or so. So that's the good news. Next slide, please. The other thing is, as I said, that efficiency has increased. And so if you take the amount of fuel burnt per passenger per kilometer, you see the downward trend since the first jet aircraft. So the Comet 4 and the 707 are top left there. If we take the Comet as 100%, then A320 is down around a fifth of that fuel burnt per seat per kilometer. So that's a massive saving. So the efficiency's gone up, the fuel burn's gone down. As I said, that was largely to do with cost. Next slide, please. Bad news is that the number of people flying has gone up massively. The number of aircraft in the sky has gone up massively. So even since the 1970s, there's been a tenfold increase in the number of passengers flying. Obviously, that was affected by COVID, but even that surprisingly fell back down to only 2003 level of passengers flying. Next slide, please. And predictions are that if nothing else changes, that upward trend is going to continue. So there's a massive increase, depending on which forecast you believe. There is always going to be an increase in air traffic. So we need to do something. Next slide, please. So this pie chart is a breakdown of fuel consumption in the US only, in terms of it's billions of gallons per year, so it's a lot. Aviation, gasoline, and jet fuel are a relatively small proportion, but they are a significant proportion. So we need to do something about that. And it's not just the amount that's being burnt, it's where it's being burnt. So burning kerosene at 30,000 feet is not a good idea because of the particles that come out of the engine from the burnt fuel, for example, and contrails that form that help affect global warming as well. Next slide, please. So as you're probably well aware, governments have snatched onto this and are incentivizing aviation companies, aircraft builders, engine companies to do something about it. So aviation needs to change. We can't carry on doing what we're doing. And so the desire to try out alternative powertrains especially has come front and center. So we're now doing it for the battle on climate change rather than to reduce costs. Included in that set of reactions has been the Scottish Government's Green Deal. which has mandated the Highlands Islands airports limited to create a zero emissions aviation zone by 2040, and that led to the setup of the Sustainable Aviation Test Environment project, which you may have seen David Holden and Dougie Cook and others talk about today as well. Next slide, please. The trouble is that there's no silver bullet to replace the burning of dinosaurs. So the most common proposed alternatives include hydrogen as a fuel, and that's in two forms: liquid at cryogenic levels or at gas. So the chart here shows the specific energy on the bottom line compared with kerosene. You can see that only ammonia comes close to that efficiency. The trouble is ammonia is quite nasty stuff. It's caustic and difficult to contain. And there are issues with hydrogen as well, and I'll come on to that in a moment. Next slide, please. So if we concentrate on hydrogen, and the other proposed alternative is sustainable aviation fuel. So that's a kerosene-like substance which hasn't, it's not a fossil fuel. It's grown from various feedstocks, including biomass. But currently the cost of hydrogen is massive compared with kerosene. So the grey line at the bottom is kerosene. It's a bit of a catch-22 situation because the amount of hydrogen being produced is quite small, so the cost is high. So it's not being used very much. So we need an economy of scale and some way to kickstart that reduction in cost. But even at scale, liquid hydrogen will be more expensive than kerosene is today. So there will be a cost implication here, even if we can solve all the technical issues. Next slide, please. It's this chart which really shows the challenges for aircraft designers. So what we have on the bottom axis is the mass energy density of fuel. So that's how much bang you get per kilogram of fuel. And on the left-hand side is the volumetric density, energy density of a fuel. So that's how much bang you get per litre, so per unit volume. So ideally what you'd like is something with a lot of energy per litre and a lot of energy per kilogram, because then it won't weigh much and it won't take up much room. So again, kerosene is in there. So that leads you to the top right-hand corner of that graph if you had the perfect fuel. Kerosene is quite good on a density, on a mass point of view, and it's very good on a volumetric point of view. Draw your attention to the bottom left, which is where you've got lithium-ion batteries. So they are neither volumetrically nor mass efficient. They are heavy, and the energy density per kilogram is not great, or per volume. So they will be limited probably to small aircraft. On the right-hand side at the bottom, we have hydrogen, liquid hydrogen and gaseous hydrogen. So they are energy mass efficient. They're on the right-hand end of that bottom curve, but they are volumetrically challenging. They're at the bottom end of the y-axis there. So these alternatives all have consequences for aircraft design, which I'll come on to. Next slide, please. So hydrogen is being proposed in two ways generally. One is to use it as a replacement for kerosene, so burn it in a combustion chamber in the same way you use kerosene or avgas now. The trouble with that is that you're still burning air, so the fuel-air mixture is still burnt, and so you're producing a lot of the particles and greenhouse gases that current gas turbines produce. The right-hand side there shows an alternative, which is one that the likes of Zero Avia are doing. They have a hydrogen fuel cell which drives an electric motor. So that's a much cleaner way of doing it, but you need to be able to refuel the fuel cell to produce, keep producing the thrust. Next slide, please. So I've mentioned the volumetric challenge. So 2 aircraft here, ATR, you'll be familiar with if you've flown with Loganair recently, and then the A320, which is the common mid-sized aircraft. So the coloured blobs there are the volume of fuel tanks that you'd need to replace kerosene. So it's not too bad on something like the ATR 72, which is short range. So the volume is bigger for these alternative fuels, but not massively bigger. That's not true for longer range aircraft like the A320, and it's even worse for intercontinental aircraft. So you can see the size, or a representation of the relative size of the fuel tanks in the coloured blobs at the bottom, bearing in mind that you need 2 of these to give you enough fuel for your mission. Next slide, please. And hydrogen's tricky stuff. It's a single molecule, which means it's really hard to keep it in one place. It likes to leak through any gaps or even through most materials. And that has issues for safety and maintenance. So if hydrogen wants to get out of where you're trying to keep it, it will collect elsewhere. So if you're doing maintenance in a hangar, for example, on a fuel tank, and you vent the hydrogen, it will find its way to the ceiling, which is where most of the lights are, and one spark will set it off. So it's very abundant, but actually getting it into gaseous form is quite hard. And it also has the nasty trick of interacting with other materials. So those of you familiar with the oil and gas industry will have heard of hydrogen embrittlement of pipelines, for example. So the hydrogen in the hydrocarbon brittles the inside of a pipe and makes it won't be able to withstand the same loads or vibration or similar things. Next slide, please. So another alternative propulsion powertrain is electric options. Obviously, as with my involvement with Ampaire last year, we flew the hydroelectric hybrid aircraft between Wick and Kirkwall, and then flew it down south, and I'll touch on that a bit more later. But in the US, NASA are looking at various electric propulsion alternatives. And the picture on the left there is a conceptual rendering of called the X57, the experimental project, also called Maxwell. And it's what we call distributed electric propulsion. So rather than having 1 or 2 big engines, there are lots of smaller ones. And that has some advantages because you're now forcing air over the wing so you can get more lift from it. The current reality is somewhat different. So the bottom right-hand picture there is the actual aircraft. It's not quite got the distributed electric propulsion, but it does have electric powertrain on it. So small steps towards a more ambitious target. Next slide, please. So have you ever seen the inside of a battery, a large lithium-ion battery cell? It is a collection of hundreds, if not thousands, of AA cells all linked together. One of the problems which you've probably all seen is thermal runaway. So once a lithium-ion battery starts burning, it's very hard to put it out. It also suffers from traditional battery ailments such as charge memory. So if you don't cycle it correctly, you can damage the cells and it won't charge fully. So at the moment, lithium-ion fuel cells are thought to have a lifetime of about 2,000 to 3,000 recharging cycles, which if you're using an aircraft every day, means that after about 6 years, you'll need a new battery. And the other big problem is the constituent materials. So in the chart on the right-hand side, there is a list of component materials within a lithium-ion battery. Some of them are rare earth elements, and the clue's in the name. So these things are difficult to get. There is a limit to how much there is of them, and in some cases where they come from is going to be a challenge. So electric is not a perfect solution in the same way that hydrogen is not a perfect solution. Next slide, please. However, there have been some notable successes. You may be familiar with the Rolls-Royce Axel world speed record, which was achieved last year. So that has 3 electric motors. You can see the silver donuts at the front on the bottom left-hand picture. They are 3 inline motors from YASA. There's a big battery pack in green behind it. And then because of the heat, you have to have some cooling, and you have to have an inverter to convert the DC battery output to AC motor input. But it's a very successful project. Hats off to them. It's quite a cool looking airplane as well, which always helps. Next slide, please. So from an aircraft designer's point of view, this chart really tells you what the problem is. So the percentage on the left-hand side is the percentage of the aircraft mass. And generally, the fuel weight, so if you take the grey kerosene line at the bottom there, the fuel weight is just between 1/4 and 1/3 of the all-up mass at takeoff. Hydrogen might enable you to have a higher or more fuel for the same mass, but then we will come on to the volume aspect of it in a bit too. And battery on the left-hand side, the battery becomes too much a proportion of the mass at anything over a range of about 500 nautical miles. So at the moment, unless somebody comes up with a new battery chemistry, which even if they do, to get it certified to fly is going to take at least 5 years, batteries are just too heavy to do anything longer than regional or sub-regional routes. Next slide, please. So the Aerospace Technology Institute is a government-funded research centre based down near Cranfield. And over the last 1.5 to 2 years, they've been evaluating the possibilities of alternative powertrains for civil aircraft transport. And they've come to the conclusion shown by this graphic here that so we have effectively range going from left to right. So sub-regional is the inter-island and maybe Inverness to Kirkwall type of routes. Regional is London to Inverness, and then you've got the longer range aircraft heading out to the right-hand side there. So battery electric is at the bottom, and that confirms the fact that that type of propulsion really at the moment is only viable for short range, smaller aircraft. Hydrogen electric, as with the Zero Avia one, will give you more range, but still not huge. And at the moment, the only foreseen solutions to longer range aircraft is either hydrogen or dropping in sustainable aviation fuel as a direct replacement for kerosene. Next slide, please. So the ATI looked at 3 different classes of aircraft, ATR 320 and 767. The last of those is interesting because that's not a new aircraft, so it wasn't a very challenging comparison in some ways. But they came up with 3 new types of aircraft. So they plumped for hydrogen, and these 3 aircraft, which are increasingly higher payload and range as you go down the page, all have hydrogen propulsion of one form or another. Next slide, please. But you remember that the volumetric problem of hydrogen means you've got to have massive fuel tanks. And so this is a section through one of those concepts, the medium range one, if I remember rightly. And you can see the green areas there are the hydrogen fuel tanks. So they are rather large. That's assuming that you can come up with materials to safely store hydrogen in an aircraft right next to a passenger cabin, that you can refuel it happily, and that it won't leak into places you don't want it to leak. Next slide, please. But we have to start somewhere, and so Zero Avia are pioneering hydrogen-fueled aircraft. and will bring their Dornier 228 hopefully to Kirkwall in the next 2 years as part of the SAPE project. We've already had Ampaire's hybrid electric aircraft, which is a modified Cessna 337. So the front engine here has been replaced by an electric motor. The rear engine is still a conventional Lycoming avgas aircraft. The reason for the 337 was because it gives you twin engine safety, but the two engines are in line, so you don't get any asymmetric control problems with an engine failure. Next slide, please. So this shows you the components of the front electric motor. So the black donut behind the spinner is the electric motor. The silver box on the slant is the inverter, which converts DC to AC. And then there's the cooling. So the actual aircraft with the cowling off is shown in the bottom right-hand picture there. You can just make out, hopefully, the silver inclined box, that's the inverter. And obviously the motor is hidden behind the cowling at the front. And underneath the aircraft is the battery pack. So that sits underneath the cabin where a luggage pannier had already been approved to sit. One of the problems we had was that obviously this setup is somewhat lighter than the Lycoming engine that it replaced, and what we would normally like to do is move some other bits around to compensate for that change in center of gravity. The easiest thing would have been to move the battery pack forward to compensate for the lower weight, but the nose gear is in the way, so we were limited to how far we could move the battery pack forward. And so in the end we had to put in a cast iron plate in the engine bay to balance the aircraft back out again. So it's the first time in my entire aircraft design life that we've deliberately added weight to an aircraft rather than deliberately trying to take it out. Next slide, please. Just some nice videos of Ampaire's aircraft. This is flying in California. It did 24 flights over a period of about a month. Nothing failed, and it accumulated 33.5 flight hours. So Ampaire are based at Hawthorne Airport in the US, in Los Angeles, which, for those of you who are an anorak like me, it's where Northrop used to be based. It's where the flying wing concepts were first developed by Northrop and test flown there. Next slide, please. So having flown well in California, the aircraft was shipped to Hawaii to assess it on real airline routes. So Mokulele Airlines in Hawaii looked at the aircraft flying on some of their internal routes. And again, over a period of about 3 weeks, it flew over 20 times, was 100% reliable, and was very successful. Watching that video, I think the Cessna 337 has probably got the ugliest rear gear retraction mechanism in the world. It looks like a dead chicken waggling its feet around at the back, which is unfortunate. Next slide, please. So that's the 337 at Kirkwall, and a view of Kirkwall Airport from the 337 during one of its forays from Wick to Kirkwall. And a big thank you to all the people at Kirkwall Airport and to Heil and others that supported us doing those flight testing. Next slide, please. So once we'd finished in Wick, we took the aircraft down to Devon and Cornwall. The aircraft was fitted with a US transponder which broke somewhere near Perth. So the aircraft landed at Perth, had a replacement UK transponder fitted, and then flew down to Exeter and did flights between Exeter, Newquay and Land's End. So the aircraft has flown literally from John O'Groats to Land's End. And that 418 nautical mile flight from Perth to Exeter was at the time a world record. It's been broken by the same aircraft flying from Los Angeles to Oshkosh to take part in AirAventure just last month. Next slide, please. So some of the perhaps more mundane challenges that exist, as with electric cars, unification and standardization of charging is going to be critical. And there's no point having an electric aircraft if you land at an airfield and you've got the wrong plug on the end of your charger. It won't fit in the wall. So SAE, who look after a lot of automotive and aviation standards, are working towards standards for electrified aircraft propulsion. A lot of that work's been done in the US, and Ampaire is actively involved in that. So it's not only just the shape of the plug, it's the voltage that you use and the safety systems around it. Next slide, please. And some of this was touched on earlier, especially with David Holden's talk around infrastructure and energy. So it costs money to install charging infrastructure for electric aircraft. It costs money to install electrolyzers for creating hydrogen. So how does an airport that has to pay for that get its money back, while at the same time not putting people off from buying and running zero carbon aircraft? Why would an airline buy a more expensive aircraft? So there needs to be a bit of carrot and a bit of stick to incentivize the airports and the airlines to use, and passengers even, to use these aircraft. And there's no point having zero carbon aircraft if that energy doesn't come from renewable sources. And one of the excellent things about flying in Orkney is that we have access to lots of green energy. There's the electrolyte, the hydrogen production plant on ED. There's lots of other interesting renewable activity going on in EMEC with wave and tidal as well. But that's not going to be so easy to achieve in other geographies, more landlocked geographies, for example, or more urban geographies. So that needs to be understood about how that entire energy system links together, especially if aircraft are competing with electric vehicles for their electricity, or, for example, if hydrogen aircraft are competing with domestic heating market to get their hydrogen. Next slide, please. And one of the things that exercised me for about a year and a half was the aircraft certification. So every single aircraft will have to have a type certificate to allow it to fly. You need to be able to prove that the aircraft was designed in the right way and is safe. At the moment, none of these alternative powertrains are covered by existing certification processes. So EASA, the European Aviation Safety Agency in Europe, and the Federal Aviation Authority in the US are looking at ways to integrate these powertrains into certification processes. And there's a bit of divergence, so it'd be interesting to see where our own Civil Aviation Authority pins its colours, whether it's to EASA or whether it's to the FAA. None of them are wrong, they're just different, and they all require different processes. So EASA, for example, are probably likely to require a type certificate for the powertrain, and then every different aircraft that use that powertrain will need another type certificate. But this is it's work in progress. And as part of the SATE project, we've had a variety of aircraft involved, and most of them have had to use legislation and certification routes that weren't appropriate necessarily to their aircraft. So Flare-Bright's small handheld UAV had to go through some rather interesting hoops to get permission to fly. Next slide, please. And then on the airport side, if you've got electric and kerosene together, if you've got hydrogen and electric together, there will need to be guidelines for the safe refueling and operation of those aircraft. At the moment, there are no guidelines. They used to exist, but they've all been withdrawn. So aircraft fueling and refueling isn't covered by any guidelines from the Civil Aviation Authority. There are some around hydrogen from the Health and Safety Executive, but that needs to be tightened up, especially where you've got fuel lines adjacent to each other in airport tarmac, for example. Now, I touched on distributed electric propulsion earlier, so more smaller engines than currently. So there are different failure cases. There are different classifications of engine. If you've got one battery but lots of motors, is that a single engine aircraft or is it a multi-engine aircraft? And what happens if you rely on the lift from those engines blowing over the wing? What happens if that stops? So lots of things still to challenge us. It's not going to get boring anytime soon. Next slide, please. But fortunately, change is afoot. These two pictures I've chosen to show how both the technology and the thinking has changed. On the left-hand side is the first ever mobile phone. That big block behind the handset is the battery. Compare it now with what's in your smartphone and the length that would last. Change has happened. And hydrogen still puts the fear of God into some people, largely because of things like the Hindenburg. But hydrogen is being used regularly now in the maritime sector, also in the automotive sector, and that confidence needs to be transferred to the aviation sector. So next slide, please. So that's me. Thanks very much for your attention, and happy to go for a grilling, as Dave said.
Well, thank you very much, Andrew. That was fascinating. I've made a note of a whole dose of different facts and figures, which I'm going to shamelessly pass off as my own after this talk, but thank you very much indeed for that. We don't really have any particular questions, and of course we've had the kind of sad news about the Queen during your talk, so I think it might be an idea just to thank you very much for your talk, and just to say that the events that we've got in the Aviation Festival for tomorrow, the talks are going to be starting at 2 o'clock with Professor Dougal Cameron and his talk on the aviation and the art of engineering. Then at 4 o'clock, there's a Robert Foden film on the story of Trygve Gran, who was the first man to fly across the North Sea. And then at 7:30, the final event in the Aviation Festival is a discussion, the Northern Battle of Britain, with Commander David Hobbs, Paul Weaver and Ian Brune and Anthony Cumming as well. And that talk starts at 7:30. But I think probably the best thing to do at the moment, Andrew, is to thank you very much. That was brilliant talk, and thank you very much for stepping in at very short notice. And thanks to all the folk listening, and there'll be more events tomorrow for you. But in the meantime, thank you very much and good night.
All right.